All right, so we've talked about combinations a bit. We've talked about permutations. One of the things that those assume, the assumption that we make when we're dealing with a permutation or combination, is that all of the items that we're choosing from are distinct. Okay? They're all different. However, if we had something like this, here's just a basic example here. We've got this word, trigonometry. And we want to arrange these letters in order. Okay? Well, you count them in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All right, so there's 12 different letters there. So if I'm arranging all 12 of those letters, how many different ways could I do that? 12. What? 12 factorial, that's right, okay? Now, the problem with this is, if I look at all those letters as kind of distinct items, then that would be correct. However, in reality, let me show you something. Here's a different permutation. Can you see the difference?
Like you switch the
You
switch the O or you switch the T.
Wait, what'd you say?
Like probably you switch the O or T, but they're the same.
Okay, yeah, you're exactly right. I was thinking about the O's, but the T's work as well. I switched the two O's. Now, technically, is that a different permutation?
No.
Yeah. Is it a distinguishable permutation? No. All right. So, we have to think, how are we going to get rid of those repeated permutations? It's similar to the concept that we used when we were deriving this formula for permutations. We said you do the n minus r factorial to eliminate the ones we don't care about. But then, what did we do to eliminate all the different permutations of the same group? We divided by the r factorial, right? Because r was how many we had. And we were just eliminating the ones that were rearranged. Well, here, notice there are two O's. So, I'm going to divide by a 2 factorial. That will eliminate the cases where I just switch the O's. Does that make sense?
Yeah. How about a T?
Okay. You're right. There are also 2 T's. So now I need to divide by a 2 factorial to get rid of all the ones where just the T's are switched. And then also, there's another R that's repeated. So I'm going to divide by another 2 factorial to get rid of all of the permutations where the R's are switched. Okay? So, how do we remove the repeated permutations? Here's the long explanation that your book gives. Okay? But what we're dealing with here is we're dealing with things where, notice, n sub 1 factorial, n sub 2 factorial, n sub 3 factorial, and so on. Okay? Those are where I was getting these 2's. And the n is how many of each distinct item we have. Okay? So for example, to use that formula with this, we had 2 T's, we had 2 R's, we had two O's, and then we had an I, a G, an N, we had one M, one E, and one Y. Okay? So technically speaking here, what we would have done is we would have done 12 factorial over 2 factorial times 2 factorial times 2 factorial times 1 factorial, 1 factorial, 1 factorial, 1 factorial, 1 factorial. How many do I have? 5. 1, 2, 3, 4, 5. 1 factorial. Now, do we need to include all of those 1 factorials? No. Those all just equal 1. We don't need to worry about those. So we usually just leave those out. Okay? And we get what we have right here. 12 factorial over 2 factorial times 2 factorial times 2 factorial. Okay? Any questions so far? Okay. Now, baseball playoffs are starting soon. Any of you baseball fans? One? Only one baseball fan? Man. All right. Well, that's surprising.
I consider not like.
Especially being South Florida. I would expect more baseball fans in South Florida.
It's more of a traditional sport. Like it's more popular. Like not back then. Like people still like just saying. Like,
Yeah.
It's offended the sport.
There is a broader range of sports that people are involved with nowadays than baseball was a cheap sport to play. All you needed was a ball and a stick and tough hands if you didn't have gloves. So just kind of dealt with it. All right, anyways, a baseball team. We have, the batting order has 9 players that can hit. All right? So we have 5 left-handed hitters. How many of you are left-handed?
You are?
All right, cool. I'm left-handed too. How many of you are right-handed? I assume the rest of you. Okay.
None of you are gonna be famous.
All right. So we have 5 left-handed hitters and 4 right-handed hitters. How many permutations of left and right-handed hitters can we make for a 9-person batting order? So, just to illustrate one of those permutations, if I wanted, I could put all 5 L's, all 5 of my left-handed hitters up first, and then have the last 4 people in my batting order be all the right-handed hitters. Okay? That's one permutation. Now, what's going to happen if I just switch these first 2 L's?
No change. The same.
It gives me a new permutation, but they're not distinct, right? They're not distinct.
If they have nan, then it's different.
If they have what?
They have different nan.
If we were looking at them as individual players, you're correct. If they're names.
Then it's 9. How do you say?
Wait, I'm sorry, what?
Permutation.
Oh, n is 9, yes. So we would have a 9 factorial.
But we need to divide it by 5 and 4 factorials.
Good. Okay. See, there are these 5 L's, 5 left-handers. Okay. So how many different ways can you arrange 5 people?
5
factorial.
5 factorial. So we need to divide by that many to get rid of them. All the different arrangements, because all we care about is which side they're hitting from. Okay? And then, how many different ways can we arrange 4 right-handers? Well, 4 factorial. Okay? So there's our solution. 9 times 8 times 7 times 6 over Alright, that's a 6 supposedly. Over 4 times 3 times 2 times 1. Alright, 3 and 2 go make a 6, so that cancels out. 4 cancels with the 8 and leaves a 2. So now we have 63 times 2 is 126. So we have 126 different arrangements when we consider just the left-handers and right-handers. Okay? So, yes. Now, there's a lot of different ways why you might want to mix things up. If you're a baseball fan, you know that, it's sometimes it's harder for a left-hander to hit when a left-hander's pitching, or vice versa, or one pitcher might be really good against right-handers, so you put more left-handers in, or you mix them up, and there's all kinds of strategy in there. But regardless of the situation, we have some identical items, so you have to eliminate those to see how many distinguishable permutations you have. Okay? Any questions? Comments? Yes?
Can you simplify factorials?
What do you mean?
Like, can you combine 5 factorial and 4 factorial? Or like, if it was 2 factorial, 2 factorial, 2 factorial, can you, like, is that the simplest way that you can put it?
I mean, technically speaking, like if you have, just like anything, if you have 3 of the same thing multiplied together, you could write that as, as 12 factorial over 2 factorial, like cubed, because there are 3 of them multiplied together. You can't do something like, make that like 8 factorial,
Okay.
or,
Yeah,
you can't combine them that way. On this one down here, if you really wanted to, noticing that 5 factorial and 4 factorial, there's only 1 factor difference. So if you really wanted to or needed to for some reason, you could rewrite the 5 factorial as a 5 times 4 factorial, and then when you multiply it by the other one, it would be 5 times 4 factorial squared, if you wanted. So you can simplify a little bit, but you can't really combine 2 factorials into 1. Okay, that's a good question though. Alright, any other questions? Okay, so quick review of combinations. Alright, we'll do one here with our deck of cards. Okay? Here we have R items out of N when order does not matter. So we have a standard poker hand consists of 5 cards dealt out of a deck of 52. Alright? How many different poker hands are possible? Now notice here, after the cards are dealt, the player can reorder them. So the order that they actually get them does not matter. Okay? So we're dealing with a combination. Order doesn't matter. So think about this one. Figure this one out on your own. Alright, so how do you have this one set up? Okay, good. N is 52.
R is 5.
Okay, R is 5, so it's 52, choose 5, right?
Mm-hmm.
How many different ways can we pick 5 cards out of the 52 if order does not matter? Okay? So you've got 52 factorial over 5 factorial times 47 factorial. Okay? Well, that's a big number. Alright. What did you get? Jake?
2,598,900.
What were the last three digits?
960.
960.
60, yeah. 60.
All right.
16 now.
So 2,598,960 different combinations of cards. All right. So again, in this case, arrangement doesn't matter. We're just putting them into a hand. All right. So, you know, here's the thing. The probability of any one of those hands is the same. So your chances of picking out 5 cards and getting the 4 of hearts, 5 of hearts, 6 of clubs, queen of spades, and king of hearts is the same as getting the 4 of clubs, ace of diamonds, 9 of diamonds, 10 of spades, and jack of clubs. You have a 1 in 2,598,960 chance of getting this hand, or this hand, or this hand, okay? All of them have an equal probability. Off of the first 5 cards, that's your chances. And like the royal flush, it's the most rare, but that's when you are, like when you have other cards coming in, it's the rarest. But the reality is, if you pick any 5 cards, you have just as much of a chance as getting a royal flush as you do
2, 9, 20, like
everything completely different. Okay? And that's because every hand has an equal probability, assuming that everything is random and whatnot. Okay? So, move away. Now, let's talk about combining multiple events. I reviewed that combination idea here because I want to look at multiple events. Here we're forming a 12-member swim team from 10 girls and 15 boys. The team must consist of 5 girls and 7 boys. Okay? So we have 12 people total. We need 5 girls and we need 7 boys. Okay? How many different 12-member teams are possible? Now let me just tell you this before we get into this one. All right, this concept here is one of the ones that people have a lot of trouble with sometimes, okay? And that's when we have this group of people, we have a total, but then we want a certain number out of one subgroup, in this case girls, and then we want a certain number out of another subgroup, which is be boys, okay? So we have 25 people total, we only want 12. So the tendency is to think, oh, well, I have 25 people, you know, so I'm going to do a 25, choose 12.
No.
Now tell me why that's wrong.
Within that 12, sure.
Go ahead.
Within 12, you can have different combinations of boys and girls from the chosen value. So, like, of the total, some aren't in, some aren't. That you're not including in that equation.
Okay. Okay. Well, how are you going to explain it, Winnie?
Because it says the team has to consist of 5 girls and 7 boys. But if we use this, then that would be just like we don't know the number of girls and the boys.
Very good. We don't know how many boys and how many girls are in those 12 people we picked. Now, this would be the total number of 12-member teams we could pick if gender didn't matter. If we just wanted our 12 best swimmers no matter what, that would be what we wanted to do, 25 choose 12. Okay? However, in this case, we've got to be specific. So here's what we've got to do. Here's our fundamental counting principle coming back into play. All right? Fundamental counting principle says the number of ways one event can happen multiplied by the number of ways the other event can happen will give you the total number of ways they can happen together. So, for right now, let's just look at the girls. How many different ways could I get 5 girls out of those 10?
Would you do 10 choose 5?
Exactly. We have 10 girls to choose from, and we want to choose 5 of them. Okay? How would we figure out how many ways we could get 7 boys?
15 choose 7.
Yeah. 15 choose 7. So, now I have the number of ways I could get 5 girls. I have the number of ways I could get 7 boys. So what do I need to do with those?
First you find what each one equals, and then you multiply them.
Okay, yeah, we're going to multiply those together. All right? We're going to multiply those together. That's our fundamental counting principle. All right? How many different ways can they happen together? Because for every one of these combinations of girls, we have this many combinations of boys. Okay? So, question?
Yeah. Why? I kind of sort of a question. Why wouldn't we just add them together? Is something already kind of mixed? Or we have to further mix them, I guess.
Well, yeah, because let's say, here's one of our combinations of girls. Here we have Sam and Winnie and Carrie and, we only have 5 girls in here. All right. Euron and Bebe. All right. So for each of those, let's say that's one of our teams for the combinations of 10 choose 5. For that, we have this many different combinations of 7 guys.
Right.
And that's just with one of the combinations of girls.
Okay.
So now every one of those combinations will have that many combinations of guys. So that's why we've got to multiply them. Okay?
Thank you.
All right. So how many do we end up with here? It's a lot, right?
First 10 choose 5 is 252.
Okay.
And I'm working on public.
Did you guys get 15 choose 7 yet?
Yeah, 6,435. I think.
All right, 6,435.
Also,
Okay, so now that we have those two, we'd multiply them together. And what's our final answer here?
5, no.
5.
1,621,620.
Okay,
Seems reasonable.
is that what someone else got? Okay, we got confirmation here. All right, so good. There's a lot of different teams that we could
Wow.
make with just choosing 5 out of the 10 girls and 7 out of the 15 boys. Okay? Yes? All right. All right. Does this make sense to everyone? Are there any questions about what we're doing here? All right. This is a very common type of problem. All right. For example, one kind of classic example with probabilities and counting and stuff is like license plates. All right. How many different license plates could we make? I remember, I think I was in high school at the time, back in Ohio. Up to that point, all the license plates had 3 letters and then 3 numbers. Okay? Well, then at some point when I was in high school, I think they were running out because then they started putting in a 4th number. Okay? Well, now if I wanted to see how many different license plates I could make, let's think about this. Oh. Let's go with the original ones. All right? If I have 3 letters, how many choices do I have for the first one? And let's assume that they can't repeat. All right, we're not going to repeat any numbers or letters. So how many different license plates could I have without repeating any of the letters?
26. Choose 3.
Yeah. Okay.
How would you get 26?
The amount of letters.
26.
Yeah.
Okay. So we're not going to repeat any letters, and we're not going to do any different permutations of the same letter. So this is just combinations of 3 letters. All right. If I were actually looking at the license plates themselves, you're allowed to have the same letter repeated twice, and the different orders change, right? So that in that case, I have 26 choices for the first letter, 26 for the second, and 26 for the third. So actually, in reality, we would have this. Okay? But this is 26 choose 3 is assuming we're never going to use the same letter twice, and the different arrangements don't matter. We just, how many different groups of 3 could we put on there? All right. The numbers, it's kind of the same way. We have 10. We could do a 10 choose 3. That would be ones where none of the numbers are repeated, 0 through 9, okay? And also the different arrangements of those wouldn't matter, all right? Now, in reality, how many different permutations would there be if the numbers are allowed to repeat?
Like 10.
I'm sorry, what?
Like 10 then 3.
Good, 10 to the power of 3, all right? If you think about it, 0, 0, 0 all the way up to 999 is 1,000 numbers. So, but it's 10 to the third. So, by the way, this shows us why it's important to pay attention to the context of your problem. All right, what are the restrictions? The reality is this. Okay. What?
10 to the third times 26.
This is the reality. I can have AAA 000 on a license plate, okay? This 26 choose 3 and 10 choose 3, I would say, okay, I don't want any of them to have the same letter repeated, and I don't want any of the license plates to have the same 3 letters in a different order, okay? But so this one is not really how they're made, okay? It's the second one that is. Did you figure out what that is?
Yeah, it's like 17.6 million, just about.
So 17.6 million about.
Mm-hmm.
So there's a lot. But if you think about it, if they've been doing it for a couple of decades, they could easily run out. So, yeah. So, all right. That's no good. All right, anyways. So, I've given you, there's some practice here. This includes more than what is required, okay? As usual, there's... Alright, what I want you to do is actually start with different ones in here. And do the required ones, okay? This is a good one here. So take some time to think about this, but I'm going to give you time to work together at this point and start with